So say you're given A as a subset of B and you have a vector bundle over B. So then you can restrict this vector bundle over A. So this is clear from a diagram. So say there's a base space B and this is a two-dimensional space, and on it you have a vector bundle like this. So say this is vector bundle E, and then you consider a subspace of the space B. So consider, say, this subspace, we call it A. So A is a subspace of B, and then you can restrict this vector bundle E over space A. So we are going to restrict this, and now this space now here, this slice right here, this is the same vector bundle E, but now it is restricted to A. So if you are given a vector bundle on a bigger space, you can always restrict it to a space which is contained in this bigger space B. Now always when you are thinking about pullbacks, so whenever you think about pullbacks, so if you pull back along this map, so A to B F, and you're given a vector bundle over B. So if you're given a vector bundle over B, it will have on every fiber it will look like this, E of B. So A goes to B via map F. So this F of A is equal to B here. So this A gets mapped here to some element B. So then if you are pulling back this vector bundle, you should think about it as fiber by fiber. For fiber by fiber, it will look like E of F of A. So this is a vector bundle on A. So notice that you're inputting A here. So this is the way to think about fiber by fiber for a pullback. So the thing connecting it is the function. So now see, you're inputting in A here. So this becomes a vector bundle over A. So fiber by fiber. So this I did not mention in the last lecture, so I thought it is a good time to mention now. So this at least I think this is good way to think about of a pullback. It gives a concrete idea of what a pullback is. Now let us talk about a sub bundle. So say you have a bundle E. This bundle E contains another bundle E prime. So say this could be of dimension n, and this could be of dimension k, where obviously k is less than n. So you could have this Rk is naturally contained in Rn, and this space B is the base space. So this E prime also becomes a vector bundle over B. So let us draw this. So say you have this base space is B, and then on B you have vector bundle, say E. So attached to this point you have this bundle, and then for every point you have these, say, two-dimensional bundles. So we cannot draw all of them, so we are just drawing some of them for presentation's sake. So you have these bundles E on this space. So corresponding to this point you have this bundle, corresponding to this point you have this, corresponding to this point you have this. So now we want to consider a sub bundle. So now I'm going to draw sub bundle. So sub bundle is this. So the sub bundle is contained in our main bundle. So E prime here, this is contained within E. So here you can see this more clearly. So say if this base point is B, then let me write in different colors. So this entire space is E of B, and this green one is E prime of B. So E of B, which is this entire white square, contains this line which is green. So this E prime is a sub bundle of E. So now we want to talk about direct sum. So say you're given two vector bundles E1 and E2 over some base space B. Then you can find their direct sum, E1 direct sum with E2. This is how it looks like, V1 comma V2, and both these vectors project onto the same point in the base space. So this vector bundle, this goes to the base space B, and these two vectors, they will project to the same base point B, and the local trivializations are taken just as h1 times h2. So h1 is acting on e1 and h2 is acting on e2. So this is the simplest possible way to take the direct sum. So let us see it more in the figure way. So say you have the base space B and you have two vector bundles on it. So this is one of the vector bundles. And then you have another set of vector bundles. So this is a bundle E1, this is bundle E2. So they are on the same base space B, and the transition functions here are H1, the transition functions here are H2. So what you're doing is obviously on the same base point you have now two vector bundles, one in yellow and one in green, and they both project vector by vector on the same base point. So they both project to the base B. And for direct sum, you do what is easiest possible. You keep this thing as such. H1 is acting on E1 and H2 is acting on E2. So you don't do anything much, you don't fiddle with it. So you just take direct sum, and local trivializations like write as h1 times h2, saying that h1 will act on e1 and h2 will act on e2, just like it was before. So that is it. So if you write this base space times e1 direct sum with e2, it will have elements of the form now b, v1, v2. So now you have three things here. So for example, if you have this sphere and you have this bundle, the tangent space, and then direct sum with the normal to the sphere. So elements of this are of the form of b, v, tb, because we talked about before the normal space is just t times the point B. Now this v and tb are perpendicular to each other. So since these two vectors are perpendicular, you can add them up and you will get a bigger space Rn plus 1. So let us see this, draw this in S2, and that will make things more clear. So this is space S2. You take a base point here. So at this base point you have two things. One, you have the tangent bundle, which goes like this, and the second you have is the normal bundle. So normal bundle is in the same direction as the base vector, so you have tb for the normal, and then you have bunch of vectors which are perpendicular to this normal bundle, which make this tangent plane. So those are vectors v. Now obviously if you take the vectors in the tangent plane and sum it with the perpendicular vector, you get the entire space R cube, because you have the plane now, and perpendicular means whatever is not in the plane is also taken, so you get R cube. So you had S2 times TS2, you took direct sum with NS2, and this is nothing but R cube, because you're taking the perpendicular vector and the vector in the tangent space. So this becomes Sn times Tsn, direct sum with normal space gives you this. So a bundle is called stably trivial. So it's called stably trivial if it becomes trivial after taking a sum with the trivial bundle. So for example, this normal bundle is always trivial because this is just t times the base space, so it is just some Rn. So since normal bundle is always trivial, so if you take the tangent space, which is non-trivial bundle, direct sum it with normal bundle, what you get is a trivial bundle. So this is trivial. So this we have talked about before. So this one is trivial. So you take tangent bundle, direct sum with normal bundle, what you get is a trivial bundle, Sn times Rn plus 1, and therefore you can say that this tangent bundle is stably trivial.